general relativity, step by step. We are gradually putting the cuffs on this metric tensor here. What we've got is a nice diagonal form for this tensor with a 3 uncertains, k, c and little k here, k, c and this little k here, that we haven't quite pinned down yet. So rather than fool around with algebra, I'm going to cheat and use maxima. So I've got my maxima here. So let's put that down there, see if I can make it a bit bigger. And we go load C tensor. Load some background stuff here. We need to specify our coordinates. CT coords R, TR, theta and phi. Brilliant. Again with the rather poorly placed commas there. Right then, and LG is a matrix. This is the metric tensor G, but with coordinates. Sorry, with subscripts rather than superscripts. And what have we got? Well, I've got the formula right here. It's going to be this one here, da 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 da, and it knows again that capital K, capital C, and little k are constants, which we will try and pin the value down of. Plus C over R, comma 0, 0, 0. That's the top line, comma 0, and then that's K over K plus C over R, 0, 0. Comma 0, 0 r squared, comma 0, 0, 0 r squared times sine theta squared. I think that'll do. Yeah, there we go. All rows must be the same length. What have I done wrong? 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Ah, there it is. Comma 0. Yes, that should work. Yes, of course, we don't know what these things are. So now we need to go C-metric, and it does some setups behind the scenes. C-metric does some stuff behind the scenes. Let me just scroll leftwards a bit so we can see the output done. And then we need to find the Ricci tensor, which is this. Okay, and a great deal of mucking around here. Now, we set this up so that we wanted to find what k and c were, k and little k and c. But you see this equation here, it's always worthwhile going to the simplest one first. We know that all the components of the Ricci tensor are identically 0, so we may as well start with the simple one. And that tells me very, very directly that, well, look, let's just write it down. 1 minus capital K over little k equals 0, so of course k equals k. That's quite nice. So that means I can rewrite this equation here to minus k plus c over r, 0, 0, 0, I guess, 0, 1 over, oh no, it's a k, k plus c over r, 0, 0, and then the other terms are here as well. Now we can make a further simplification by simply rescaling our radius and our time, our radial coordinate r and our time. So I can just assume that k equals 1. We can just change k. We can just multiply everything by a constant if we want, and everything works out. So I'm just going to say k equals 1. Right, what have I got left now? I've got minus 1 plus c over r, 0, 0, 0, 0, 1 over 1 plus c over r, 0, 0, 0, 0, and I think that's r squared, and here's the azimuthal component, r squared sine squared theta. There it is. So again, we're gradually putting the cuffs on it. So task, find capital C. What is that C? Well, it's going to be a function of mass. Everything here is driven by mass, and that sounds like quite a difficult thing to do. If you'll remember how hard it was to find that undetermined constant in the Einstein field equations, this might sound like a total nightmare, but it isn't. It's relatively straightforward. We've got a nice form for our metric tensor here with one uncertain parameter, this capital C here, which was a constant of integration from, I don't know, 3 or 4 pages back. Let's find out what C is. Stop.